Hello, dear students. Welcome to our channel Only Physics JEE Grad. Today, in this video, we'll be discussing JEE Advanced PYQs from the chapter Electrostatics. Now, this will be the fourth video on this chapter, and the topics will be covering our potential energy, right? So, there will be a total of 78 questions on this topic, and today we'll be discussing 17, I guess. Okay. Further questions will be discussed in next videos. So let us start with our first question. So this is our first question. Now this question is quite interesting. So we have a thin spherical insulating shell of radius r carries a uniformly distributed charge such that its potential at the surface is V naught. So we have a circle, and it's a shell, right? So it's a shell, not circle, it's a shell. And the charge is distributed uniformly over it. So let's call it sigma. And the potential at the surface is V naught. So inside it, the potential will also be V naught, right? So V naught is everywhere. Now this whole of small area is made shell without affecting the, okay, perfect. So here there is a hole right here, right? So area of this hole is sigma, so alpha pi r square. Alpha pi r square is the area of it, right? So it's a quite small area. Now, in the first option, there are other options also. Let me put them. So there are other options like this. Okay. So we need to choose which option is correct, right? So this is quite interesting question. Now, the ratio of potential at the center of the shell to that of the point at 1 by r from the center towards the hole. So let's call this point O and let's call this point P. So we need to find the ratio of the potential. So VO by VP we need to find, right? Perfect. So look, if there was no hole, the potential at center was V naught, right? Now, so V naught is how much we can find it. So it will be KQ by R, right? And let's say it's sigma, the charge density is sigma. So we can write it as sigma Q into pi R square sigma. So it will be sigma into pi r square, right? So Q will be sigma into pi r square, right? Sigma into area upon capital R, right? So this will be the V naught. Now we need to find the potential. So it will be V naught dash and VP dash, right? And so it will be equal, right? Before cutting this hole out. So potential inside will be equal to the surface. So V naught equals to VP and everything was equal. Now this hole is made. So what happens is we need to remove the potential due to this small area, right? Now the question comes, how much potential we have to remove from the center, from the O, right? So look, if this is very small, in the question it is given it is a very small area, right? So if it is very small, then this particle behaves like a point charge, right? So let's call this charge has Q Q1 charge, right? So how much it will be? So it will be sigma into alpha pi r square, right? Quite easy. So we need to remove the potential due to this. So due to this, it is at a distance r from the center, right? So V naught dash will be V naught minus K Q1 by R, right? Divided by VP. Similarly, at VP, we'll do the same thing. VP initially the potential was V naught, right? So it will, let's call it VP minus K Q1 by R by 2, right? So this is quite simple. So V naught minus KQ1 by R. So KQ1 by R, we can write it as K sigma alpha 4 pi R square divided by R upon. And now VP is same as V naught. So we'll just write it as V naught minus K sigma alpha 4 pi R square again divided by R by 2. Now look, K sigma 4 pi r square by r is V naught. So we'll just write it as V naught minus, this will be V naught into alpha. So V naught into alpha, right? Right? Divided by, so this will be V naught minus V naught into 2 alpha, right? So this 2 is in denominator of the denominator, so it will become numerator of this, right? So it will be 2 alpha. So if you take V naught as common, so it will be 1 minus alpha upon 1 minus 2 alpha, right? It's quite simple. A will be the option, right? But this question is quite interesting, right? Let's check too. The potential at the center of the shell is reduced. Actually, this question, in this question, only one option is correct. So we'll get a other options are wrong, but we should check other options too, right? So let's check. The potential at the center of the shell is reduced by 2 alpha V naught. So at center it is reduced by alpha V naught. So this option is wrong. The magnitude of electric field at the center of the shell is reduced by alpha V naught by R. So let's check. Look, when the hole was not made, so how much the potential will be? So how much the electric field will be, right? We need to find this. How much it will be? So it will be 0. So initially we can write E at O is 0. Now after the hole is made, right? So what happens? So what happens? The electric, there will be electric. So I have to remove the electric field due to this, right? So I have to remove electric field due to this. So let's remove it. So it will be, let's say it will be E naught dash. So it will be E naught minus the, I have to remove it. So it will be K Q by R square. All right, K Q by R square. So E naught was 0. So minus it will be K we can write it as 1 by 4 epsilon naught. So let's write it K as K, right? Because all the answers we need to find in terms of V naught. So it will let it be K, and so it will be Q1, right? So Q1 will be sigma alpha 4 pi r square divided by r square, right? So E naught dash will come out to be K sigma 4 pi r square divided by r. It's V naught, so it will be alpha V naught by r minus alpha V naught by. So it is reduced by alpha V naught by r, not alpha V naught by 2r. So this is again wrong. Next, the magnitude of electric field at a point located on the line passing through the hole and the shell center on the distance 2r from the center of this spherical shell. Okay, so let's check. Right. So magnitude of electric field at a point located on the line passing through the hole and shell center. So let me make a line here. So this is the line we're talking about, right? And where the point is? So the point is on a distance 2r from the center of the spherical shell, right? So 2r, so this point can be here, P1 can be here, and P2 can be here, right? So these points. So look, the thing is at P1 and at P2 it will be different for both the cases, right? Because due to shell, electric field at P1 and P2 will be same, right? But when you subtract the field from this, so at P2 and at P1 it will be different. So actually answer won't be same. So this is wrong, of course, right? Because here it is reduced by a simple K sigma by R square, right? And here it will reduce by K sigma by 2R square. Okay. So K Q1 by 2 R. So it will be so it will be 3R square. So it won't be same. So D option is absolutely wrong. So only A is correct, right? Let's move on to question number 2. So we have our second question with us. So this again is quite interesting question. So we have two large vertical parallel metal plates having separation 1 centimeter. So they are vertical, right? Connected to a DC source having potential difference X, right? So let me make the diagram, right? But these are vertical actually, right? So let me rotate them. So these plates are like this, right? Perfect. So now uh, they are connected by a DC voltage source of potential X. So it's potential X. The proton is released at rest in the midway between the two plates. So in the mid, let's say the separation is D. So at a distance T by 2 from the either plates, the charge is released and it is proton. So let's say it has charge Q. It is found to move a vertical just after the release 45-degree to the vertical. So let's write like this. So this is our vertical and it moves like this, right? And look, it so this plate has charge plus capital Q and this will have minus Q because it is connected to the lower potential, right? So the proton must go in this way. And why it is going in the 45? Because there is a mg force acting downward and a electrostatic force must be acting like this, right? And if they are moving at an angle 45-degree, then that means this electrostatic force must be equals to gravitational force, right? So let's find the electrostatic force. We know electric field between the plates is sigma upon epsilon naught, right? And the charge is Q. So Q into E we have written here, and this will be equals to mass of proton into G. Okay, now we need to put all those values here. Right. Okay, so let's put all those values. So we need to find X. So let's convert this electric field in potential, in the terms of potential. So how can you write electric field between the plates? You can simply write V by D, right? So we'll just write V by D, and V is here O X, so X by D. So let's just write it as X by D because we need to find the X, right? Into small q, into Q. So Q we can write it's proton, right? So it's proton, where it is? Yes, it's proton. So charge on proton is simply 1.6 into 10 raised to power minus 19, right? Now mass of proton. So mass of proton is how much? So we can take it as 1.6 into 10 raised to power minus 27 kgs. Okay, and G we can take 10 for simplification. So, okay, the separation is also given. So D is 1 centimeter. So we can write, okay, so it is so D is how much? So D will be 10 raised to power minus 2 meters, right? So X will come out to be 1.6 into 10 raised to power minus 27 into 10 upon 1.6 into 10 raised to power minus 19, and D will get multiplied, which is 10 raised to power minus 2. So let's cancel the things out. So this will get cancelled, this will also get cancelled, and this will be 10 raised to power minus 8, right? And this is how much? 10. This is 10 and plus 1, so minus 9. So it answer will be 10 raised to power minus 9 volts simply. So C option is correct. Okay, so again, quite an easy question we have. Let's move on to our third question. So we have our third question. Consider a thin spherical shell of radius r with center at origin carrying uniform potential, positive charge. The variation of magnitude of electric field and potential with the distance r from the center. Oh, so this is quite easy, right? So if we have a shell, the electric field will be 0 till capital R, and then it will jump, right? So it will jump, and yes. So how much it will be? It will be kq by r square, and then it starts to decrease, right? Like this. So this is E versus R graph, And V versus R, we know potential from here to here it will be same. It will be constant, which is KQ by capital R, and then it starts to decrease, right? So which of these graphs represent it? I think D represent, right? So this is not, because electric field should not be like this, right? So D will be the option. Okay, these two are not possible because they are linear, right? Like increasing linearly. So this is for the spherical, the electric field, right? Okay, let's move on to our fourth question. Now, in our fourth question, we have a system of three charges at A and B, Q by 3, right? So here we have Q by 3, and here also we have Q by 3, and at C we have minus 2Q by 3, shown in figure. Okay, so question is missing. Let me put the other half of the question. Right, perfect. From the figure, as shown in the figure, O at the center, okay, CAB is 60 degree, perfect. The electric field at O is directed along x-axis. So let's make the diagram. So we have a sphere like this, and let me make the lines. So this is our first line, this is our second line, right? And this is our third line. Perfect. Okay. And this is our center. Here it is A, the charge is Q by 3. At B, again, same charge Q by 3, but at C, the charge is minus 2Q by 3, right? And this angle is given 60 degree. Perfect. So at the center, we need to find, so we must understand that at center, electric field due to A and B will be 0, right? Okay, so first of all, it's given that this is x-axis. So this we have as the x-axis, and this we have as the y-axis, right? Okay. Now in the question, it's saying that electric field at point O is directed along negative x-axis. So of course it is directed along negative x-axis, but due to A and B it will be 0. So due to C it will be K 2Q by 3 upon R square, because this distance is R square. Look, C point is along the x-axis, okay? So how much it will be? So it will be 1 upon 4 pi epsilon naught 2Q by 3 R square. So it will be 2 and 6. So it will be 6. So A option is wrong, right? The potential energy of the system is 0. The potential energy of the system is 0. Let's check. So when A was here, there was no potential. Then B we took. So potential energy will be KQ by 3 into Q by 3 divided by 2R, right? Then we bring the point charge C. So due to C and A, so potential between C and A will be K Q by 3 into minus 2Q by 3 divided by this distance. Okay, so we need to find these distances also. Right, so let's find. So look, this is 2R. Okay, let's join these lines. So this must be R. So if this is R, this is R, then this will be also R. So it will be 60. This will be 60. And if this is 60, and this will be 120. And you know, this is R, this is R. So these two angles must be equal, right? Angle opposite to equal sides are also equal in the triangle. So it's 120. Then we are left with 60. So this must be 30. This must be 30. So this becomes 90, right? So it's quite easy. If this is 2R, then this will be 2R cos 60, and cos 60 is 1 by 2. So this is R. Okay, so this was, we know this was R, right? Now let's find this. So it will be 2R cos 30. So it will be root 3R, right? Quite easy. So A and C. So R, A, C are right, and plus the potential energy between B and C will be K Q by 3 minus 2Q by 3 divided by distance between BC. So RBC, right? Okay, quite easy. Perfect. Let's put those values here. So it will be, so KQ by 3. So RAC is how much? So it will be R, and this will be R by so root 3R, right? So we'll just take common KQ by 3 whole square divided by R. Let's take it a common. Here we're left with 1 by 2. Here we're left with 2. Okay, and here we are left with minus 2 by root 3. So this will not come out to be 0. So B is wrong. Okay, B is wrong. Okay, let's move on to C option. So what is C saying? That force between the charges C and B. So between them. So force between them will be K Q by 3 2Q by 3 divided by distance between them will be root 3R square. So it will be 3R square, right? So this will be 1 upon 4 pi epsilon naught 2Q square by 3. This will be 27, right? R square. Okay. So 333, right? So this will be 2, and it will be Q square by 54. 54 pi epsilon naught R square, right? So C option is okay. So you can check D option must be wrong. So potential due to A and B will get cancel out, and we're left with potential due to C only. So it will be at O, it will be KQ, so minus 2Q by 3 divided by R, right? So it will be 1 upon 4 pi epsilon naught, so to 6 pi epsilon naught Q by R. So with negative. So this is again wrong. Okay. So quite interesting, quite easy question. Just we need to use the property of a triangle. Let's move on to our fifth question. So we have our fifth question with us. Okay, perfect. So here we have a long hollow conducting cylinder is kept coaxially inside a long hollow conducting cylinder. Okay, so do we have the shape here? No, right. So let me put this one here. So this is our long cylinder. This is our smaller cylinder, right? Perfect. And let me put the lines like this. Okay, perfect. Coaxially, both the cylinder are initially electrical neutral. Okay, so we have to choose the points. A potential difference appears when the between the two cylinders when a charge density is given to inner. So if let's say it is given sigma, the potential difference between the two cylinders appear between the two cylinders appears, right? So is this correct? Like if the sigma is given, then the this part of the cylinder, right? It does not matter even if it is here, right? There will be electric field here. Okay, so electric field will be here, right? So even if you consider this as a cylinder, let's say this has a sigma. Okay, so here the some charge density will appear minus sigma, and plus sigma will appear in the outside, sigma dash you can consider it, right? So there will be electric field, right? They will behave like a capacitor. Okay, so there will be electric field due to these, right? And as they are conducting, due to minus sigma dash, there will be not electric field here, right? So electric field will be there. So A option is correct. Okay, so as it is single correct, A option is matching. So but let's check Other options, a potential difference appear between the two cylinder when the charge density is given to the outer cylinder. So again, look, this is quite interesting. If you give a charge density sigma to the outer sphere, all the charge will go to the outer surface, and inside there will be no electric field. So B option is wrong, right? So there will be potential, but potential difference will not be there. Okay, no potential difference because electric field is zero, right? So you just need to check the electric field. If electric field is zero, then potential difference is zero. So if electric field is not zero, then there will be potential difference. So potential difference will not be zero, right? So no potential difference appear between the two cylinder fan. Uniform line charge is kept along the axis of the cylinder. So it's like this. So if there is a line charge, then there will be electric field, right, in the region. So there will be potential difference. So this is wrong, right? So no potential difference appear between the two cylinder when the same charge density is given to both the cylinder. Okay, so now this question option is quite interesting. Let's give both of them sigma. Okay, uh, right, where are we? Okay, sorry for that. Now this cylinder is given sigma and this is also given sigma, right? Now what happens? So C was wrong, right? Okay, C was wrong. Now no potential difference appears between the two cylinder and the same charge density is given to both the cylinder, right? So what happens now? Look, on this curved surface, let's say there is a Q charge here. So, right, so Q will be here. So minus Q will be here, right, due to a polarization, right? So if minus Q is here, then here it will be Q dash plus Q, right? So Q dash plus Q. Now due to these charges, there will be electric field again. Okay, are you getting me? Look, if the sigma is the same, then what happens? These surfaces are of different curved surface area, right? So charges will be different. So I'm saying that Q is here, so it will be minus Q. So on the outer sphere, it will be Q dash plus Q. So even if they have same sphere, if they have same surface area, the charges will be same. It does not matter even, right? So there will be polarization here, and due to this, there will be electric field. So D option is again wrong. So if there is electric field, the potential difference will be there. Right? So guys, D option is wrong. Okay, quite interesting question. Let's move on to our sixth question. So we have our sixth question with us, and there must be options. Let me put those. Okay, so there are no options. No worries. So let's first solve this, our sixth question. So we have a positive and negative charge of equal magnitude kept at this point, and the work done by the electric field when another positive charge moved from this to this. Okay, so let me fix the axis like this. Okay, so this is our x-axis, this is y, and this will be our z. Now these two charges are placed like this. One is here, one over here. So this is positive at 0, 0, a by 2, and this is negative 0, 0, minus a by 2, right? Work done by positive charge placed at minus a. So let's call this point as minus a, 0, 0, and this point is our 0, a, 0. Okay, so we need to find the work done. For that, we must know the potential. So potential at A, so let's call this point as A, let's call this point B. So potential at A and B will be same, right? Because this distance and this distance is equals to this distance and this distance. So potential at A and B is same, so work done will be 0. Right, so this is quite easy. We don't even have to solve it. Let's move on to our seventh question. Okay, perfect. So in seventh question, we have 2 point charge fixed on these axes. So let's call this x equals to a. Let's call this x equals to minus a. We have two equal charges, so q, small q. Another point charge q is placed at origin. So capital Q is placed at origin. The change in electric potential energy Q when it is displaced by a small distance x along the x-axis. So let's move it here like this. Okay. So look, initial potential difference was right 0 because it will be double, right? It will be due to this and this because there are two equal charges. It is not one is negative and one is positive, right? Uh, so if I displace it by distance x, so this distance will be a plus x and this distance will be a minus x. Okay, change in potential energy. So let's first write initial potential. So initial potential was 2kq by a, right? Now final potential will be kq by a plus, so yes, it's right? Okay. So kq by a plus x plus kq by a minus x. So let's write change in potential energy. So it will be q, capital Q, v final minus v initial, right? So q, let's write. So let's first solve this. So it will be kq upon a square minus x square, and this will be a plus x, a minus x. So x will get cancelled, so it will be 2a. So we can write it as 2kq 2a upon a square minus x square minus this will be 2kq upon a. Okay, let's take things common. So it will be 2kq capital Q are common. So we'll left with 2. So 2 is we have took it as common. So it will be a upon a square minus x square, and this will be minus 1 by, right? So on solving, you will get a square minus a square plus x square. So it will be 2kq capital Q x square upon a square minus x square. Now, as x is very small compared to a, of course, so we can write delta u as, we can ignore this x square. So it will be 2kq capital Q x square by a square. Okay. So the potential energy is proportional to approximately x square. Okay. There are options. Let me put those. So no, there were no options. I don't have the options, but this will be the answer. Okay. Let's move on to our next question. Question number 8. Right. So we have a uniform electric field pointing in x direction exists in a region A, B origin. So A is origin, and we have electric field like this. Okay. And we have a B point on x-axis at a distance like this. So this is P, this is 1, 0, and we have a C point on y-axis. This is C point, so this will be 0, 1, right? Then the potential at A and B satisfy this. Okay, so this is quite easy. The direction of electric field potential drops. So VA must be greater than VB. Now, as it is uniform electric field, so let's call this point as D. So at D and B, potential must be same. So VD equal to VB. And at D, it must be less. So VD should be less than VC. Okay, so which option is correct? So as VB and VD are equal, so we can write VC is greater than VB. So these two are the relations. A is wrong, so B is correct. Okay, this so V at A is equals to V at C, right? Hmm? Wrong and wrong. Okay, so only B is the right option, right? So quite interesting question it is. Let's move on to our next question. Question number ninth. Okay, perfect. So there are three charges shown in figure. Electrostatic potential energy is zero. Then Q is okay. So it's quite simple. Let's write the potential energy. So between these two, it will be K Q square by A square. And this is isosceles. So this is A, this is A, this will be root 2A, right? Plus between these two, so it will be K Q small q by A square. And between these two, it will be K Q by root. Oh, okay, I have written force here. Sorry, by my mistake. So we need to write the potential energy. It will be K Q1 Q2 by R, right? So it will be not 2. This will be 0. So K Q will get cancelled. A and A will get cancelled. So we are left with Q is equals to minus Q will take common. It will be 1 plus 1 by root 2, right? So Q will come out to be root 2q minus upon root 2 plus 1, right? So if you multiply and divide by root 2, you will get minus 2q upon 2 plus root 2. So B is the correct option, right? Let's move on to our 10th question. Right. So we have a non-conducting ring of radius 0.5 carries a total charges distributed non-uniformly on its circumference. Electric field everywhere in the space. The value of integral. Okay, so this is quite easy. We know this is a small ring, right? Compared to infinity, the potential at infinity we need to take it as a zero, and potential at this we need to find, because this is what this is V 0 V at center minus V at infinity, which is simply VO because this is 0, right? So this integral is equals to this. Okay, this is final limit, this is initial, so this is this. So we just need to find the potential at the center, right? So potential, and look, it is a non-conducting ray and the charge distributed non-uniformly, so it does not matter. Let's say we have dq1 here, this is dq2, so V at center will be K dq1 by R plus K dq2 by R and up to so on. And you solve it, you'll get KQ by R summation dq. And this will be K R by R into Q, right? So we can just find it. So K will be 9 into 10 raised to power 9 into Q is 1.11 into 10 raised to power minus 10. It's quite easy question it is, right? 2.5. So this will be 10 raised to power minus 1, and this will be 9.99 divided by 5 into 10 raised to power minus 1. So this will get cancelled, and this is almost 10 by 5, which is plus 2, right? Charge is positive or negative, carries a charge this. Okay, so it's positive, so A will be the option. Okay, quite easy again. This is the definition, right? You should understand. And in the definition, minus will also there. Okay, so be careful. Let's move on to our 11th question. Perfect. So we have two charges held fixed at this point in a xy coordinate system. Let me make it. So let me call this as x and this as y. So we have 2 point charges. Here it is plus q and here it is minus q. Okay, this is minus d comma 0 and this is D comma 0, right? The electric field E at all the points on the x-axis has the same direction. So this is quite wrong, right? So here in this region, let me make those regions for you. So we have three regions, this, this, and this region, right? Okay. So in this region, electric field will be in this direction. Okay. So here, the electric field will be in this direction, right? So this is the direction of electric field I'm writing. And here, the electric field will be in this direction. So it will not be in the same direction. This is wrong, right? Electric field at all the points on the x-axis is along x-axis. So along x-axis means in the positive x-axis. So here the field we know that definitely it will be along either plus x or minus x. Let's check. And we must know the dipole is toward minus q to plus q. So this is the dipole moment. And on the y-axis, we know electric field will be in this direction at all the points, right? Okay. So is B option correct? Electric field at all the point on y-axis is along x-axis. So B is correct. Okay. Work has to be done in bringing a test charge from infinity to origin. So in at infinity, V at infinity is 0 and V at center is also 0. So work there is no work to be done. So this is wrong, right? Dipole moment 2qd is along x-axis. So no, it is along minus x-axis. So again, this is wrong. Right? There is an ambiguity, so it is along x-axis. So this is x-axis, right? It is not clearly mentioned that it is plus x or minus x. So we'll just consider it like that. Okay. Let's move on to our 12th question. Okay. So we have a hollow metal sphere of radius 5 charged with the potential on its surface 10 volt. The potential at the center. It will be 10 volt, right? Again, this is quite easy. Okay. So this was our 12th question. Let's move on to 13th question. Okay, so there must be some options. Let me bring right. Okay, let me zoom in. Perfect. So this is our 12th, this is our 13th question. Okay. Now there are six charges placed like this. This is our X charge, right? All are placed on the perpendicular from the near hexagon, the center is bisected by it. Okay, perfect. So this is bisected by it. So, okay, perfect. Now which of the following is Q? Is true. So when X is equals to Q, the magnitude at center is 0, right? It will be 0. So let me find these distances. Look, this is A, this is A by 2. So this distance, let's call it D. So D will come out to be under root A square minus A square by 4. So it will be root 3A by 2. Okay. So remember this distance. So this distance is root A by 2. So we need 2D. So 2D will be root 3A. Okay. So all the charges are at distance root 3a. Okay. So A is correct, right? The net field at the center will be 0. Okay. Let's move on to second option. When x is minus q, the magnitude of electric field at O is this. So when it is at minus q, so electric field due to A, these two charges will be 0, these two charges will be 0. This charges electric field will be in this direction, and due to this charges electric field will be in this direction, right? So it will be 2e. Okay, so let's find this due to one charge. It will be k q by r square. R square will be root 3a square. So it will be 2 upon 4 pi epsilon naught q upon 3a square. So this will be q upon 6 pi epsilon naught a square. So yes, B option is also correct. For the C option, the potential at O when it is 2q. Now it is 2q is this. Okay. So due to these five charges, the potential will be simply 5kq by root 3a. Perfect. Yes. Due to this charge, it will be k 2q by root 3a. Okay. So let's add them. So it will be kq by root 3a. We can take it as common and it will be 7, right? So it will be k. So k we can write it as 1 by 4 pi epsilon naught root 3a into 7q. So 7q upon this 4 pi, right? So C option is also correct. Okay. Now similarly, if this is minus 3q, then it will be minus 3. So it will be 2kq upon root 3a. So it will be 2q upon 4 pi epsilon naught root 3a. So this will be 2. So 2 root 3 will be there. So it will be root 3 upon 4. So this is wrong, correct? So this is wrong. Okay. So ABC will be the option. Let's move on to our 14th question. Right, 14th question. So we have in a shaded region of a distance 1 when electrostatic charge density varies like this. Okay. And in the spherical shell B, the outer radius is RB. The electrostatic charge density varies like this. So look, the charge densities are different. So here it is like this. Let me change the color. Okay, so it's different. So let's find the total charge on sphere A. So it will be QA, it will be integration rho A 4 pi r square dr. Charge we need, right? We definitely need charge. So rho A will be kr 4 pi r square dr. So it will be k 4 pi and this will be r to the power 4 by 4 from 0 to 1. So it will be k pi simply, right? So this is q. Now let's find QB. So integral it will be 2k by r 4 pi r square dr. So 1 r will get cancelled and this will be 8 pi k integral. So this will be r dr and we'll get 8 pi k r square by 2. Now what will be the limit, right? So limit will be from 1 to small r. Okay. So this is quite interesting. 1 to small r p. Let's call this. So this will be 4. So it will be 4 pi k rp square minus 1. Okay, so be careful by putting this limit. So after 1 the charge density is changing, right? Perfect. So let's put those values and we'll find the options which are correct. So if rb is root 3 by 2, so it will be 3 by 2, so this will be left with 1 by 2. So for first option qb is 1 by, so it will be 2 pi k. Okay, and always qa is always pi k, right? Now the electric field is 0 everywhere outside B. Of course not, the charge will add up, so it will be due to pi k and this will be 2 pi k, so A is wrong. For B, RB is 3 by 2, so this will be 9 by 4, so 9 by 4, so it will be 5 pi k. So for this option QB will be right. So 9 by 4 minus 1, so it will be 5 by 4, 4 will get cancelled, so Q will be 5 pi k. Okay. The electric potential just outside the P will be due to this, so it will be K QA just outside the P. So distance is 3 by 2. Okay. Plus due to B, it will be QB upon 3 by 2. So this is 1 upon 4 pi epsilon naught. So let me write it as 4 pi epsilon naught. This will be 4 pi epsilon naught. So we'll get 1 by 4 pi epsilon naught 3 by 2. We'll take it as common and QA is pi k, and it will be 5, so it will be 6 pi k. So pi will get cancelled, and this 2 will go here. So this 2 will get cancelled from here, and this will also get cancelled, and we are left with k upon epsilon naught. Okay, so yes, B is correct. Right, so B is correct. Let's check the C option. So if RB is 2, total charge configuration is 15 pi k. So if you put 2 here, so we will get 4 minus 1, 3, and this will be 12. So QB will be 12 pi k. So 12 plus 1, 13. So this is wrong. Okay. Now if you put 5 by 2 here, the magnetic field just outside the B is 13 pi k. Let's check. So if you put 5 by 2, we'll get 25 by 4 minus 1. So it will be 21 by 4, and 4 will get cancelled. So for that, QB is 21 pi k. And just outside the P, let's find the electric field. So it will be due to smaller sphere. So smaller sphere electric field will be K QA upon 5 by 2 square plus. For that it will be K QP. So let's not write K again because we might get confused. So we'll just write it as 4 pi epsilon naught. Okay. So 4 pi epsilon naught and 5 by 2 whole square. So look, 4 will get cancelled here and will be 25. So we'll just write it as 25 pi epsilon naught QA plus QB. QA plus QB will be 22 pi k. Okay, pi will get cancelled, so it will be 22 k upon 25 epsilon naught. And pi will also be not there, right? Okay, is this correct or not? Yes. Okay, so this is again, so only B option is correct. Right, an interesting question. Let's move on to our 15th question. Right, so we have our 15th question. So we have a disk of radius r with the uniform charge density sigma. So we have a disk like this. Let's call this as the center. Oh, okay. Coulomb potential. Okay, perfect. So potential is given. Vz will be sigma upon 2 epsilon naught root r square plus z square minus z. Okay, perfect. So let's call this point as z. So let's call this point as P at a distance z. Particle Q is placed at rest at z equal to z naught. So let's call this z naught. It does not matter. In addition to Coulomb force, the particle experiences a vertical force in this direction. So there is a force. This is minus C. It's like mg. Okay. Okay. So we'll not consider it as mg, but it's like that. So minus is saying that the force will be in this direction. So if this is z, then force will be in minus z direction. And beta is given. So beta is 2c epsilon naught upon q sigma. Okay. So if beta is this, particle will reach at origin to return back to z equals to z naught. Okay. And is there other option? So let me check if there is other options. Okay, give me a second. So there must be some other. Okay, so there is other option D for beta greater than 1 and z naught greater than 0. Particle particle reaches origin. Okay. So first let's check A, B, D option for now. Okay. Now what happens? Look, this disk is pushes in this direction, right? So this will the electrostatic force which is uh, experienced by this. Okay. Now at P point there will be some potential energy. right? UP, it will be due to this force, right? So this force as well as this force. Okay, so what will be happening is look, this force is decreasing the potential energy. Okay, so this force is decreasing the potential energy, right? And this force, now as this particle goes in the downward direction, let's say it goes, so this force is increasing the potential energy, increasing the potential energy. And we know a system will always move towards when the potential energy, change in potential energy decreases. Okay, so that this decrease must be greater than this increase. Okay, so uh, we'll write, look, first, let's say this is some constant force, so we'll write Fk. So we'll write delta U due to force is constant force. So Fc will write. So due to Fc, right? So it will be minus C. So C is the constant force and distance it is moved by Z naught. So it will be minus C Z naught. And so this is delta U1. So delta U2, it is due to electrostatic force. Okay. So this will be positive, right? So here uh, potential is this, and at this point potential is, so Z is 0, so it will be sigma R upon 2 epsilon naught. So how much it will be? So it will be, right, so this is more. Okay, so this is more and this is less, right? Perfect. So look, in the direction of electric field potential decreases, so this is less, this is more, right? So how much it is? So it will be sigma R upon 2 epsilon naught minus this. This will be sigma root R square plus Z naught square minus Z naught upon 2 epsilon. Okay, perfect. So if you add them, so delta should be less than 0 and just add them. So delta U will be delta U1 plus delta U2. Right? So delta U1 plus delta U2 should be less than 0. So delta U1 will be minus CZ naught plus, this will be sigma upon 2 epsilon naught. This will be R plus Z naught minus root R square plus Z naught square should be less than 0. Okay, so CZ naught will go here. So we will be left with, so let me write it over here. So we'll be left with sigma upon 2 epsilon naught R plus Z naught minus root over R square plus Z naught square should be less than C Z naught. Okay, C Z naught. Now beta is what? So beta is 2C epsilon naught upon Q sigma, right? And we need to multiply it with the Q also, right? Because we are writing potential is Q, and this will be Q. So look, this will whole become beta. So it will be simply R plus Z naught minus root R square plus Z naught square should be less than 2C epsilon naught Z naught upon Q sigma. And this is actually beta, right? So this is actually beta. So we're left with R plus Z naught minus root R square plus Z naught square is equals to sorry, less than beta Z naught. So this Z naught will go here and this R will go here. So left with, so let's put this here, this here. So we'll get root R square plus Z naught square. So this will be R plus Z naught 1 minus beta, right? So this is the final. We can of course square it, but the problem with the square is it will take some points, some positive and negative values out from the solution. Okay, so I'm not squaring, I'm just putting it like this. So let's check A, B, D option first. Okay, then we'll check C. So for C, the particle written, so we'll check later. Okay, so first let's put beta is 1 by 4 and Z naught 25 by 7R. Okay, so it will be 25 by 7 and beta is 1 by 4, so this will be 3 by 4. So this will be R plus 25 by 7R into 3 by 4, right? So if you calculate this, it should be less than root R square plus 25 square. So 625 R square upon 49. Okay. So if I use the calculator really fast, so this comes out to be, so this will be 75 plus 28. 75 plus 28, it's 103 divided by 28. So this will come out to be 3.679 something, okay, R. And this will be 625 plus 49, right? 674, and I need to take the root of 674. So it will be 25.96 and we have to divide it by 7. So this will come out to be 3.708. Okay, so look, this thing is really messing us. So is this greater? Yes, it is greater. So the particle reaches origin. So A is correct. Okay, let's check B. Okay, so Z naught is now 3 by 7. So I'll write it as Z naught as 3 by 7 and beta is again 1 by 4. So if you put those values, you'll get R plus 3 by 7 into 3 by 4, right? R is less than R square plus Z naught. So it's 3 by 7 R. So it will be 9 by 49 R square, right? So how much it will be? So it will be 9 plus 28. So this is 9 plus 28. It is 7 divided by 28. So it will be 1.321 R. It's less than this. So we'll just write it as 49 plus 9, which is 58, right? So root 58, and I have to divide it by 7. So it will come out to be 1.08 R. So of course this is wrong. So B option is wrong. Okay. Now, now let's check D option first. So if for beta greater than 1 and Z not greater than 0, particle reaches origin. So if beta is greater than 1, so this is negative and Z not greater than 0. So let's put those values. So this will be R minus. So if this is greater than 1, so this will be negative. This is Z naught. And we're left with, so this will be Z naught can be anything which is related to R. So this will be R minus this less than, and this is root R naught square plus Z naught square. So look, this value is greater than R naught, and this value, look, this is subtracting from R, so it is less than R, and this value is always greater than R, right? So this value is always less than R and this value is always greater than R. So automatically D option will always be correct because this value will be always more than this. So the D option is also correct. Okay, now let's check the C option, right? Okay, so look, if this relation is right, then particle will reach origin, right? And then it further starts to go down. But if this relation is not correct, then particle will turn back around. So let's check. So for this, we'll need to check in this equation again. So this will be, let me change the pen. So it will be r plus, this is z naught r by root 3, and this will be 3 by 4, right? Okay. So let's make this root 3 itself. So this will be 4 plus root 3 divided by 4. So this value is 1.3433, which is less than, let's check, put z naught r by 3. So this will be uh, 2r by root 3, right? 2r by root 3. So 2 divided by root 3. So this will be 1.154. Okay. So this is smaller, right? So as it is small, so particle will not reach at origin. Particle will not reach at origin, and in the midway it will turn back. So the particle will turn back to. So this is correct. Okay. So A, C, and D options are correct. So this question is quite uh, conceptually it is fine, it is good, but calculation wise is extremely lengthy. Okay. So let's move on to question number 16th. Okay, perfect. So we have a point charge just placed outside this spherical surface. We have the circumference of the flat surface is an equipotential. So of course, is this correct? Yes, the circumference of the flat surface. So these points. So these points are always at equal distances, right? Right, so situation is like this. So this is a surface and we have this. So these points are all at equal distances, so A option is correct. Okay, so it is at equipotential points, right? Circumference, the points on the circumference. The component of electric field normal to the flat surface is constant over the surface. So no, this is wrong, because this point and this point, the distance are not equal. So P is definitely wrong. Total flux through the curved surface of the flat surface. Curved and the flat surface is Q upon epsilon. No. So total flux through curved and flat is 0, right? Because they don't enclose any charge, right? So C is wrong. The electric flux through the curved surface, right? So whatever be the flux through curved, it will be the same. So whatever be the flux in through the curd, it should be out. So let's check. So we can write flux as Q upon epsilon naught into area. It will be 2 pi r square 1 minus cos phi, right? Divided by 4 pi r square, right? We write like this. We use the concept of solid angle. So let's check. So I'm just finding the flux through this flat area. So this flat area, okay. So let's check. So this is just this distance is r, and this is our phi angle. So phi is actually 45 degree. So let's put all those values. So it will be q upon epsilon naught. So this will be 2 1 minus 1 by root 2 by 2. Okay, so it will be root 2 minus 1. Okay, so this will be simply q upon 2 epsilon naught 1 minus 1 by root 2. So this is the flux through this flat circular, uh, right, base. We call it base. Okay, so this flux is going out like this with the area. So for the curved surface, the area will be must be like this, and flux electric field is like this. So flux should be negative for it. So D option is correct. Okay, so whatever be the flux getting in the curved surface area, it is getting out from the flat surface area. Okay, then only the total flux is zero. Okay, so the option is correct. Let's move on to the last question of this session. Right, so this question is quite interesting. This question is quite interesting. Let me zoom in. Perfect. So we have two non-conducting sphere R1 and R2 carrying uniform density plus rho and minus rho respectively. They partially overlap as shown in the figure. Okay, at a points in the overlapping region. So we'll consider, like, let's say this is a point P. So we need to find electric field, and if we know electric field, we can definitely find the potential. Okay. So let's say this is C1, this is C2, and this, let's join them. So electric field here will be in this direction, electric field will be here and in this direction. Okay, towards the center, and it will be away from the center. Now the question comes here, what happens to the overlap region? Look, they are non-conducting. So charge distribution will not change, right? In the non-conducting, charge will stay when it is placed. So if I place Q here, charge will stay here, it will not move. That is the concept of non-conducting, right? So in the overlap region, even if they are overlapping, the charge distribution won't change, okay, because they are non-conducting. Okay, so let's find the electric field at P. So electric field at P due to C1 will be rho. Let's call this as R1 vector, and this is R2. So this will be R2 vector, right? So rho R1 vector upon 3 epsilon naught, and E at P due to C2. Yes, due to C2, what it will be? So it will be towards the C2, right? So it will be rho R. So let me write the triangle first. So let's call this is origin. This is R1 vector, and this is C1 C2 vector. Let's call this. So this is capital R vector. Let's call. Okay. So this is C1 and this was C2, right? So this vector will be R2 vector, right? So how will we write it as R1 vector plus R2 vector will give us C1 C2 vector. Okay, perfect. So this will be simply R2 vector upon 3 epsilon, right? Let's add them. So electric field at P will be electric field at P due to C1 plus electric field at P due to C2. So it will be rho upon 3 epsilon naught R1 vector plus R2 vector, and we know R1 plus R2 vector is C1 C2 vector. So rho C1 C2 vector upon 3 epsilon naught, which is constant. So electric field is constant in magnitude C, right? Electric field is constant in magnitude. Electric field is zero, wrong. Electric potential is constant. So we need to check the electric field is constant in magnitude at every point inside this region, right? Electric field has same direction. So look, electric field is constant. So if electric field is in this direction, then potential will change. So potential is not constant, right? Electric field has same direction. So this D also is correct. Okay. So this question is quite interesting. Our 17th question, right? It is conceptual, and we must understand the concept of this two non-conducting sphere. Right? The charge distribution won't change. Okay. So let's finish today's video. Thank you.